This is video 36 in the lectures on the design of reinforced concrete beams. This lecture is about an example of how to calculate the seg of a beam. Consider a cross-section of 600 by 300 millimeters with a compression and a tension reinforcement. The relative humidity is 50%. The load in the characteristic value of the load is 10 kN per meter for the mobile loads and 20 kN per meter for the permanent loads. The beam is loaded after 28 days, and we are now trying to find out what is the long-term seg at midspan of the beam. We start with the long-term modulus of elasticity of the concrete, and for that we need to calculate the creep coefficient, the behavior of the concrete due to in the long term. The creep coefficient is not given. We can estimate it, calculate it, and we do it with H0, which is the proportion of the total area divided by the area that is exposed to air. Because we don't know much detail of this beam, we suppose that the total area of the beam is in contact with air. So U is 600 plus 300 times 2, that's the total surface, and this is the cross section 600 times 300. So H0 is 200. The contribution of the humidity is then given by this formula, and if you put in some numbers, you find this is 1.855. The contribution of the concrete strength, the C30, 37, gives you 2.725, and then the contribution of the time of loading, T0 in days, it's 28 days, it's 0.488. So the creep coefficient at time of loading 28 days on long term is a multiplication of those three previous coefficients and gives you 2.5 as a creep coefficient. This is in the order of 2. We know that the creep coefficient is between 1 and 3, most of the time around 2. So 2.5, that's in the line of expectation. It's a little bit high because of this surface in contact with the air. The mean modulus of elasticity of concrete is then equal to 32,800 megapascal. The effective E modulus of concrete is ECM divided by 1 plus phi. We calculated phi, so it's 9,471. Again, it is around 10,000 megapascal, which is an expected value. And then alpha is ES divided by ECF, and gives us 21.12. This is high. Normally we expect an alpha value in SLSQ, we expect an alpha value around 15. This is 21, it's still okay, but we should be aware this is high. The non-cracked cross-section, we consider first D, the effective depth, is 600 total depth minus point of gravity of the tension reinforcement minus the stirrup diameter minus the concrete cover gives us 437.5 millimeter. The D2, the position of the point of gravity of the compression reinforcement, is then the concrete cover, the diameter of the stirrup, and the point of gravity of the compression reinforcement, which gives us 57 millimeters. The depth of the neutral axis of the non-cracked section can then be found by calculating the point of gravity for the effective or for the fictive cross section. It says the concrete section and then plus alpha times the steel section. It's just if we put in the numbers, we find 327 millimeters. So the depth of the neutral axis is more than half of the total depth of the section. The moment of inertia for the non-correct section is then equal to 7.4 10 to the power 9 millimeter to the power 4. The seg can then be calculated by the simple elastic formula of 5 divided by 384 times the load L to the power 4 divided by AE. And AE is the stiffness of the non-correct section, because we are calculating here F1, the seg of the non-correct section, and it is 5.5 millimeters. Now we do the same for the correct cross section. The depth of the neutral axis is now 235 millimeters, and the moment of inertia is now 4.3 10 to the power 9. We see that the we see now that for the correct section, the depth of the neutral axis is 70% of that of the non-correct section. And we see that the moment of inertia is only 60% of the non-correct section. So the correct section is less stiff, much less stiff than the incorrect section. The seg of the correct section, F2, is then equal to 9.4 millimeters. Now we look at the cracking moment. The cracking moment is calculated with the mean concrete tensile strength, which is 2.9 megapascal. Cracking moment is then the FCTM times W. Take care, W is calculated with the non-correct section, with the depth of the neutral axis of the non-correct section and the moment of inertia of the non-correct section, and it's 78 kilonewton meter. The applied bending moment in ULSQ, quasi-permanent, equals the permanent loads plus Psi2 times the mobile loads times L squared over 8. It's in the midspan, the maximum bending moment, gives you 103.5 kilonewton meter. It means that the section is cracked. The coefficient, zeta, is then a function of the stresses, sigma SR and sigma S2, which we can replace by bending moment. And those bending moments we have just calculated. So the coefficient zeta is 0.716. Beta is 0.5, and 0.5 is for the long-term seg of the beam. For the short-term seg of the beam, it is 1. So the long-term deflection of the cracked section is then a linear combination between F1 and F2. And if we put in the numbers, we have 8.3 millimeters. Now, let's have a summary. We take a summary of the seg of an uncracked cross-section. It's 5.5. For the cracked cross-section, it was 9.4. And for the linear combination, it is 8.3. But if you now calculate the seg of the beam just as it was elastic material, and you use ECM, just the mean modulus of elasticity, and as moment of inertia, the BH to the third divided by 12, which a lot of engineers do, calculate the seg like that, and you have 2.2. You see that you severely underestimate the seg of a beam if you only use the elastic calculation methods. You should at least calculate the seg with EC equals to ECM divided by 3. Now let's make a graph of the x-axis. It's days, 50, 100, 150, 200 days. It's the days that the concrete is there, the days before loading. Let's put it this way. Here you load after 100 days. Here you load after 50 days. On the y-axis, it's the long-term seg of the beam. Now you see immediately on this curve that if you load the beam very quickly, the seg on long term is bigger than if you load it after, for instance, 200 days. The seg on long terms for the same load is smaller. And the red line here is the linear combination that we have found of 8.1 millimeters. So loading at an age smaller than 28 days has its consequences for the expected long-term seg. So don't forget that. The seg of a beam can be doubled considering a cracked section, or even triple. See you at next lecture.